Hello, welcome back to the course Physics 2, and we will continue discussing the topic of geometrical optics in this lecture. And here we will be concerned with spherical surfaces, reflection and refraction from spherical surfaces. The topics that will be covered hopefully in this lecture will be reflection from a spherical surface. The definitions will be introduced. The concave mirror will be considered as a problem, and the convex mirror, and the sign convention that we use for the distances. And we will obtain the mirror equation and derive it in a final form. We will see how the image is constructed in a spherical surface. The lateral magnification of the image will be derived, and then we will consider the problem of refraction at a spherical surface. Sign convention will be introduced in the beginning, and then convex surface will be addressed. The concave surface also will be discussed, and the refracting surface equation will be derived, and finally the lateral magnification will be obtained for the refraction from a spherical surface. And to begin with, we consider the reflection from a spherical surface, and the spherical surface could be either concave or convex, and this picture here shows a concave mirror or spherical surface. And we start with some basic definitions that are necessary for the geometrical optics of this system. First of all, the radius r, which is this between C and P, is the radius of the sphere from which this part or this mirror is cut, and C is the center of curvature of the mirror, which is the center of the sphere from which it was cut, and O, this point, is the vertex of the mirror or the surface, and OC is the axis of the surface. S here in this figure is the object point. This is an illuminating object. And S prime, capital S, that means capital S prime, is the image point. With these are small s and small s prime and small a prime are distances of the various things, of the image point and the object point. The A's, A and A prime, are the distance of A is the distance of the object point with respect to the center, and A prime is the distance of the image point with respect to the center, while the S is the distance of the object point with respect to the vertex, and S prime is again the distance of the image point with respect to the vertex. So these are the same distances, but with respect to two different points. Either they are measured with respect to the vertex or with respect to the center C. And now we consider the concave mirror, and we see here from the geometrical relations that the angle phi prime, which is this angle here, the angle that the ray from P to S prime makes with the axis, phi prime, is simply equals to pi minus phi minus 2 theta. Here, this angle, 2 theta. And this can be rewritten as, this is alpha. Alpha is equal to phi plus theta. So this can be written as phi prime is equal to pi minus alpha minus, in parentheses, alpha plus theta. And phi as we mentioned, is equal to simply alpha, which is this angle here that the radius makes at the point where the ray from the object hits the mirror. It's alpha minus theta, minus this small angle theta here. And we apply the law of sines to the triangles SPC. This is the first triangle, SPC. And the second triangle is CPS prime. So we consider these two triangles and we apply the law of sines to these. And the law of sine applied gives r divided by a, the distance of the object a, is equal to sine alpha minus theta over sine theta. And if we expand this into sine alpha cosine theta minus cosine alpha sine theta, this gives sine alpha cotangent theta minus cosine alpha. And similarly, r over a prime, the distance to the image point, is equal to sine alpha plus theta over sine theta, which is equal to sine alpha cotangent theta plus cosine alpha. These are essential equations that we need for the mirror equation. And here, in this figure, we see that all the rays that are emerging from the object hitting the mirror, they are reflected at different points. And alpha naught is the maximum angle that the edge of the mirror makes with the axis, as the figure shows. And thus now the previous relations can give the relation a prime is equal to r times a over r plus 2a cosine alpha, which is the relation between the distance of the image in terms of the radius of curvature of the mirror and the distance of the object, and it depends on the angle alpha. We notice that there is an angular dependence alpha on of the position of the image point. And this equation is called the concave mirror equation. Now, as we said, there is in the concave mirror equation, the image point depends on the angle alpha, which means that there will be different images formed for the same point on the object, and this causes blurring of the image, so it will not appear as a point image like in the object, and this is called spherical aberration. It's the blurring that is coming from the spherical shape of the mirror, which arises from the angular alpha dependence of the image distance or the image position. Spherical aberration, however, can be reduced by decreasing the angular aperture, what we call the angular aperture to alpha naught, where alpha naught is the angle, the maximum angle to the rim of the end of the mirror. So if we consider a small mirror in dimension, that 2 alpha naught, which is this angular aperture, is very small, this will decrease the aberration, the spherical aberration of the mirror. Or vice versa, instead of considering the angular aperture alpha naught, we can think of the lateral aperture, and which is the linear aperture. So instead of considering the angle alpha naught, we consider the linear aperture, which is the height given by 2h is equal to 2r sine alpha, where each h that was shown in the previous figure is equal to r sine alpha naught. This is called the linear aperture of the mirror. So if we decrease that, we decrease the angular aberration, the spherical aberration of the image. And in order also to in order to reduce the aberration, we use paraxial rays. Paraxial rays are these rays that make very small angle with the axis, and they lie very close to the axis itself. And those paraxial rays, they form a very sharp image. So in the paraxial approximation, we use paraxial rays with paraxial approximation applied to the equation of the mirror. And we mean by paraxial approximation that the angle is very small. What does it mean? It means that alpha naught in terms of radians is smaller than 0.1 radians, which is 0.1 radians is equal to 5.7 degrees in these units. And for such rays with very small angle, the cosine alpha is very close to 1 because alpha is very small. And thus, we replace cosine alpha in the equation by 1. And we get this relation, which is A prime is equal to R times A over R plus 2A. So this is the mirror equation, the paraxial approximation. And this figure shows, again, the mirror with the relation. If we want to write down now the mirror equation in terms of the distances S and S prime measured with respect to the vertex rather than the distances A and A prime measured with respect to the center of curvature, then we use the relations A is equal, this A here with respect to the center is equal to S minus R, the radius R, and A prime is equal to R minus S prime. So with these introduced into the formula that we derived a little while ago, so instead of A and A prime, we write S and S prime, and the relation is 1 over S plus 1 over S prime is equal to 2 over R, where R again is the radius of curvature of the surface. Now, this is the mirror equation written in a different way. For the convex mirror, we use the very similar argument, where here we define the angle phi double prime, which is the angle, this angle that the ray from the image makes with the axis, and the radius is called R double prime here because it's in the dark region of the mirror. This is the bright region of the mirror here, and C is the curvature as typical. And the distances, we call them A double prime and S double prime in order to distinguish them from those in the convex mirror, in the concave mirror case. S is still S, the same S, which is the distance of the object from the vertex, and A is still the same A, which is the distance of the object from the center. So notice that as the ray hits the mirror surface, it is reflected. It's reflected that way. So it appears as if it is coming from this point, actually. So this would be the image point. But the ray appears as if it's coming. So this is an imaginary point, actually. And here we use the same trigonometric, similar argument using trigonometric functions, and R double prime using the law of sines. R double prime divided by A from this big angle here is equal to the sine of the angle, this angle, phi, which is theta minus alpha, divided by sine of this angle, which is the same as theta. This is equal to cosine alpha minus sine alpha times cotangent theta. This is r double prime over A. And similarly, r double prime over A double prime, which is obtained from this triangle here, PCS prime. So this r double prime over A double prime using the law of sines is equal to sine theta plus alpha divided by sine theta. These are the relations, and this is after we expand sine theta plus alpha is equal to cosine alpha plus sine alpha times cotangent theta. This is the second relation that is necessary to derive the mirror equation, and putting these together, we get the convex mirror equation. A double prime is equal to r double prime times A over 2A cosine alpha minus r double prime. Bearing in mind the different parameter, r double prime is the radius of curvature. This is the convex mirror equation. Now, this equation looks somehow similar to the previous equation, but if we use some sort of sign convention, before we do this, we first of all derive the paraaxial form of this equation, of the convex mirror equation. In the paraaxial approximation, again, cosine alpha is of the order of 1, in which case the relation is A prime is equal to R double prime, A double prime is equal to R double prime times A divided by 2A minus R double prime. And this equation looks very similar to the equation in the case of the concave mirror, with some sort of sign differences instead of negative, positive in certain cases. And now we derive this equation in terms of the distances with respect to the vertex, that is S and S double prime, instead in terms of S and S double prime, instead of in terms of A and A double prime. And putting these relations into the formula that we just derived in the paraaxial approximation, we get the result 1 over S double prime minus 1 over S is equal to 2 over R double prime. This is the convex mirror equation in terms of the distances with respect to the vertex. And now we use the sign convention because the equation looks similar to that of the concave mirror. If we always assume as sign convention for our treatment that light is always incident from the left, in our problem, we consider always light incident from the left, and we consider that the object distance S is positive if the object is real. That means if the light emerging from the object is diverging in the form of diverging rays, as we have talked about in the previous lecture, and S is negative if the object is virtual, meaning if the rays coming from the object are converging into the mirror rather than diverging. So if we consider this sign convention for S, and we also consider that the image distance S prime is positive if the image is real. That means if the rays are converging into the image point. And it is negative if the image is virtual, meaning if the rays appear as if they are diverging from the image point. So if we put these sign conventions together, and finally we take into consideration the radius of curvature. The radius is r is considered positive if the surface produces a real image from a real object, and negative if the surface produces a virtual image from a real object. Or, in different words, if r is in the bright side, in the direction of the object, then r is considered positive. And if r is in the dark side of the mirror, in the other side, in the opposite side of where the object is, then the radius r is considered negative. With these signs in mind, with this sign convention in mind, the convex mirror equation, which is 1 over s double prime minus 1 over s is equal to 2 over r double prime. This is converted using the sign convention. It's converted into 1 over minus s prime, because in the case of the convex mirror, s double prime is negative, and minus 1 over s is positive, and the radius in the convex mirror is in the dark side, in the opposite side of where the image point is. So r double prime is replaced by minus r. So this gives minus 1 over s prime minus 1 over s is equal to minus 2 over r. So we have a minus sign multiplied by the equation. We can multiply by minus sign, and we arrive at exactly the same equation as for the concave mirror. And this equation is indeed the same as that for the concave mirror, which is 1 over s plus 1 over s prime is equal to 2 over r, which is correct now for both mirrors, but we have to take into consideration the right sign of the different variables, s prime and r. And as a special case, for example, for a plane mirror, in the case of a plane mirror, it can be viewed as a cut out of a sphere which has an infinite radius. So if we put r as infinite, 2 over r is 0, then 1 over s is equal to minus 1 over s prime, in which case s is equal to minus s prime, meaning that the image point made by the plane mirror is virtual. The image is virtual, and because it has to s prime has to be negative in order to have it equals to a positive quantity s, minus a negative quantity is positive. And the distance of the image point from the surface of the mirror is exactly the same as the distance of the object point from the mirror surface. And special case, the object is on the axis at an infinite distance. If the object is on the axis at an infinite distance, then s is equal to infinity, 1 over s is 0, then s prime is equal to r over 2, which is f equals to small f, which is the focal length. So an infinitely distant object produces an image at the focal point. And 1 over f, the inverse of the focal distance, is called the dioptric power of the mirror, and it is measured in units of diopters, where 1 diopter is equal to 1 meter to the power minus 1 over meter. Actually, this is a measure of the power of the mirror. We call the power of the mirror. And the mirror equation thus can be rewritten as, in terms of the focal length, as 1 over s plus 1 over s prime is equal to 1 over f. Again, the sign convention applies to this equation. And now we look into these two mirrors, and the rays that are traveling parallel to the axis are converging into the focal point f. And similarly, rays that are hitting the convex mirror surface, they are reflected, if they are coming parallel to the axis, they are reflected as if they are diverging from the focal point. So in both cases, for an infinitely distant object, the image is at the focal point, but in the case of the convex mirror, it is imaginary because the rays are diverging from the image point. And in the case of the convex concave mirror, the image point is real. The construction of the image is done by ray tracing, by what we call ray tracing. So we trace actually two intersecting rays are enough to identify the position of a point, but we can take any three rays of the four principal rays to locate the image of any point, of any corresponding to an object point. And those four rays that we can take any group of them to locate the point in space is, first of all, a ray that is parallel to the optic axis is reflected through the focal point. That ray, that is one of the principal rays. A second principal ray is a ray going through the focus, is reflected parallel to the optic axis. That is a second ray. A third ray is a ray through the center is reflected back upon itself. That is a third ray. And the fourth principal ray that we can take into consideration in constructing the image is that a ray to the vertex from the object point to the vertex is reflected with equal angle on the opposite side of the axis, just like being reflected from a plane mirror. Those are four rays, and we can take any set of them to locate our image. And this figure here shows an object, an extended object. And in order to construct the image of this extended object, we take 2 points. One point is at one of its ends, and the other point at its beginning. We have dealt with the problem of locating the image point of an object point on the axis, which is this tail of the arrow, for example, here in this case. Now, this is known. It is lying on the axis. It stays on the axis, as we have mentioned. But now, in order to construct the whole image, we locate the image corresponding to the head. If we locate the image of the point corresponding to the head, then we can describe the location of the whole object, the image of the whole object. So these are the four rays. One ray is parallel to the axis, reflected across the focus, the focal point. A ray going through the focal point is reflected parallel to the axis. A ray that is going through the center is reflected upon itself, and a ray that is going to the vertex is reflected with an equal reflection angle. And similar for the case of the convex mirror case. And this leads us to the discussion of the magnification, the lateral magnification, because the image that is produced could be enlarged or could be shortened. It could be inverted, or it could be erect. So for the case of the concave mirror, for example, the magnification can be derived by the ratio of the height of the image, y prime, to the height of the object y with a negative sign because the image here is inverted. So minus y prime over y is equal to a prime over a. That is from similar the similar triangles. So we have y prime over y with a negative sign is equal to a prime, which is this distance, the distance of the image with respect to the center, is divided by the distance of the object with respect to the center, divided by a, which is equal to r minus s prime over s minus r, as we know from these relations between a prime, a and r, s and s prime. And this gives the result that the magnification, the lateral magnification, is equal y prime over y, which is equal to minus s prime over s. So this is a formula for the lateral magnification in the concave mirror. And for the convex mirror, similarly, same relation holds. Y prime over y, this time the image is upright, so it's positive, is equal to a double prime over a, which is equal to r double prime minus s double prime over s plus r double prime, which is equal to s prime minus r over s minus r, which is negative of what of the previous one. This gives the same relation exactly as for the concave mirror. M is equal to y prime over y, which is equal to minus s prime over s, which is exactly the same relation. So we summarize by saying that the magnification equation applies for both mirror surfaces. M is equal to y prime over y is equal to minus s prime over s. It applies to both equations, and thus we conclude that a real image, the real image is, in the real image, s prime is positive, and s of course is positive. So in this case, in the real image, m is negative. Negative, that means y prime is negative because y is positive. So that means it is inverted. The real image is inverted. And vice versa, a virtual image, in the case of a virtual image, s prime is negative, so negative times negative is positive, in which case y prime is positive. That means it is upright. The virtual image is upright, it's erect, while the real image is inverted. This is a consequence. And now we talk about refraction at a spherical surface. And in this, here at the right at the beginning, we introduce the sign conventions. And for the sign conventions, as we have discussed in a previous lecture, in this case, s is considered larger than 0, the distance of the object, and s prime is greater than 0, according to the sign image that is adopted previously. Here, s is greater than 0, but s prime is smaller than, is negative, because the rays are diverging from the image. And here, s is negative because the rays coming from it are converging, and s prime is positive because the rays are converging into s prime. And here, in this case, both s and s prime are negative. So we keep that sign convention in mind, and s prime is positive to the right of the vertex. So if we consider a surface, a refracting surface, s prime would be positive if it is in to the right, to the opposite side of where the object is. If it's to the right of the vertex. And the radius is positive if the surface is convex to the incident rays. That means if the center of curvature is also of the surface is also to the right, opposite to the side of where the object point is. And now we consider the convex surface. Convex surface looks like this, with the distances as we have adopted previously. For s, the distance between the object point and the vertex, and S prime between the image point and the vertex, and so on. And the A's are as before. And in this case, using also the law of sines, L, this L here, from S, it's the length SP, L divided by A, which is this distance here, the position of the object with respect to the center, is equal to sine alpha, this is alpha, divided by sine theta, this is theta, and L prime, similarly, L prime divided by A prime, which is this, again using the sine law, is equal to sine alpha divided by sine theta prime. With these relations in mind, and Snell's law, also using Snell's law, n sine theta is equal to n prime sine theta prime. Putting these equations together, we get the relation n times A over L is equal to n prime A prime over L prime. And using the relations between A prime, and S prime, and the radius of curvature, where A is equal to R plus S, and A prime is equal to S prime minus R, replacing these in order to get a different form of the equation in the paraaxial approximation, using the paraaxial approximation, where in the case of the paraaxial approximation, the rays are very close to the axis, which means that L is very close to S, and L prime is very close to S prime. And also, which means that alpha is very small, and OD is negligible. This distance OD is negligible. So we use these approximations, and we conclude that the relation becomes n, the refractive index of this first medium from which where the object is located, over S plus n prime over S prime is equal to n prime minus n over the radius of curvature R. And in the case of a concave surface, also we use similar argument, but we have to keep in mind, to bear in mind, the sign convention that in this case R is negative and S prime is negative, and the equation is n over S plus n prime over S prime is equal to n prime minus n over R, with the sign convention in mind. This is for the concave. Thus we conclude that the same equation, the same shape of equation applies for both surfaces, but we have to remind ourselves always of the signs of the different parameters in the equation. And we notice that the image location does not depend on the angle, which means that we don't have spherical aberration in the case of the refraction at a spherical surface. We don't have spherical aberration, but because the equation depends on n, the refractive index, and the refractive index is dependent on the frequency of the light or the wavelength of the light, then the different frequencies or the different wavelengths, which means the different colors, appear at different locations. So the image appears blurred and sort of colorful. It's colored and blurred. So there is a chromatic aberration. There is a chromatic aberration due to the different indices of refraction for the different wavelengths. And here at this point, we have to remind ourselves that a refracting surface has two focal points, not only one, like in the case of the reflecting surface. And the first focal point, called F, is the axial object point whose image is at infinity. So we consider the equation, the refracting surface equation, and we put the image S prime at infinity. So the location of the object n over F plus 0 is equal to n prime minus n over r. So the location of the first focal point, or the first focal length, is simply nr over n prime minus n in terms of the radius of curvature and the indices of refraction. And the second focal point, f prime, is the axial image point of an object point at infinity, where the object point is set at infinity. This point, n over infinity plus n prime over f prime, is equal to n prime minus n over r. And this gives the second focal length, f prime, is equal to n prime r over n prime minus n. And the refracting surface equation is thus written in terms of the focal length rather than the radius of curvature, as n over s plus n prime over s prime is equal to n over f, or n prime over f prime, same thing. And now the lateral magnification of a refracting surface, and here we draw the refracting surface as straight. We don't care whether it is convex or concave, meaning it could be convex or concave. And in the case of this surface, where the rays are diverging, forming a real object, in this case the magnification m is equal to y prime over y is equal to minus n s prime over n prime times s, with these parameters as defined previously. And similarly, for the case where a virtual image is formed by a refracting surface, the same exact relation for the magnification can be derived and can be shown to be m is equal to y prime over y, which is equal to minus n s prime over n prime s, together with the sign convention that we have defined before being borne in mind. At this point, I would like to end my lecture, and I thank you for your attention.